Section 2.5. Standardized hash functions. We mentioned SHA-256 in our previous example, which is only one of the hash functions we can use. Before we go ahead and list the recommended hash functions of our time, let's first mention other algorithms that people use in real-world applications that are not considered cryptographic hash functions. First, functions like CRC32 are not cryptographic hash functions, but error-detecting code functions. While they helpfully detect some simple errors, they provide none of the previously mentioned security properties and are not to be confused with the hash functions we are talking about, even though they might share the name sometimes. Their output is usually referred to as a checksum. Second, popular hash functions like MD5 and SHA-1 are considered broken nowadays. While they were both the standardized and widely accepted hash functions of the 1990s, MD5 and SHA-1 were shown to be broken in 2004 and 2016 respectively, when collisions were published by different research teams. These attacks were successful partly because of advances in computing, but mostly because flaws were found in the way the hash functions were designed. Deprecation is hard. Both MD5 and SHA-1 were considered good hash functions until researchers demonstrated their lack of resistance from collisions. It remains that today, their pre-image and second pre-image resistance have not been affected by any attack. This does not matter for us, as we want to only talk about secure algorithms in this book. Nonetheless, you will still see people using MD5 and SHA-1 in systems that only rely on pre-image resistance of these algorithms and not on their collision resistance. These offenders often argue that they cannot upgrade the hash functions to more secure ones because of legacy and backward compatibility reasons. As the book is meant to last in time and be a beam of bright light for the future of real-world cryptography, this will be the last time I mention these hash functions. The next two sections introduce SHA-2 and SHA-3, which are the two most widely used hash functions. Figure 2.6 introduces these functions. Section 2.5.1. The SHA-2 hash function. Now that we have seen what hash functions are and had a glimpse at their potential use cases, it remains to be seen which hash functions we can use in practice. In the next two sections, I introduce two widely accepted hash functions, and I also give high-level explanations of how they work from the inside. The high-level explanation should not provide deeper insights on how to use hash functions, because the black box descriptions I gave should be enough. But nonetheless, it is interesting to see how these cryptographic primitives were designed by cryptographers in the first place. The most widely adopted hash function is the Secure Hash Algorithm 2, or SHA-2. SHA-2 was invented by the NSA and standardized by NIST in 2001. It was meant to add itself to the aging Secure Hash Algorithm 1, or SHA-1, already standardized by NIST. SHA-2 provides four different versions, producing outputs of 224, 256, 384, or 512 bits. Their respective names omit the version of the algorithm: SHA-224, SHA-256, SHA-384, and SHA-512. In addition, two other versions, SHA-512-224 and SHA-512-256, provide 224-bit and 256-bit output, respectively, by truncating the result of SHA-512. In the following terminal session, we call each variant of SHA-2 with the OpenSSL CLI. Observe that calling the different variants with the same input produces outputs of the specified lengths that are completely different. Nowadays, most people use SHA-256, which provides the minimum 128 bits of security needed for our three security properties, while more paranoid applications make use of SHA-512. Now, let's look at a simplified explanation of how SHA-2 works. The exclusive OR operation. To understand what follows, you need to understand the XOR, or exclusive OR, operation. XOR is a bitwise operation, meaning that it operates on bits. The following figure shows how this works. XOR is ubiquitous in cryptography, so make sure you remember it. Exclusive OR or XOR, often denoted as this symbol, operates on 2 bits. It is similar to the OR operation except for the case where both operands are 1s. It all starts with a special function called a compression function. A compression function takes 2 inputs of some size and produces one output of the size of one of the inputs. Put simply, it takes some data and returns less data. Figure 2.7 illustrates this. Well, there are different ways of building a compression function. SHA-2 uses the Davies-Meyer method, see Figure 2.8, which relies on a block cipher, a cipher that can encrypt a fixed size block of data. I mentioned the AES block cipher in Chapter 1, but you haven't learned about it yet. For now, accept the compression function as a black box until you read Chapter 4 on authenticated encryption. SHA-2 is a Merkle-Damgard construction, which is an algorithm invented by Ralph Merkle and Ivan Damgard independently that hashes a message by iteratively calling such a compression function. Specifically, it works by going through the following 2 steps. First, it applies a padding to the input we want to hash, then cuts the input into blocks that can fit into the compression function. Padding means to append specific bytes to the input in order to make its length a multiple of some block size. Cutting the padded input into chunks of the same block size allows us to fit these in the first argument of the compression function. For example, SHA-256 has a block size of 512-bit. Figure 2.9 illustrates this step. Second, it iteratively applies the compression function to the message blocks using the previous output of the compression function as the second argument to the compression function. The final output is the digest. Figure 2.10 illustrates this step. And this is how SHA-2 works, by iteratively calling its compression function on fragments of the input until everything is processed into a final digest. Note: the Merkle-Damgard construction is proven collision-resistant if the compression function itself is. Thus, the security of the arbitrary length input hash function is reduced to the security of a fixed-size compression function, which is easier to design and analyze. Therein lies the ingenuity of the Merkle-Damgard construction. In the beginning, the second argument to the compression function is usually fixed and standardized to be a nothing-up-my-sleeve value. Specifically, SHA-256 uses the square roots of the first prime numbers to derive this value. A nothing-up-my-sleeve value is meant to convince the cryptographic community that it was not chosen to make the hash function weaker, for example, in order to create a backdoor. This is a popular concept in cryptography. Warning: while SHA-2 is a perfectly fine hash function to use, it is not suitable for hashing secrets. This is because of a downside of the Merkle-Damgard construction, which makes SHA-2 vulnerable to an attack, called a length extension attack, if used to hash secrets. We will talk about this more in detail in the next chapter.